Hi, this is Dr. Green, and we are looking at some examples for the Session 5 homework. So these examples should correspond to the same number of problems in the homework, and there are written solutions also under the homework help link on Blackboard. So let's go ahead and get started. So in this first problem, they want us to graph an exponential function, 1/4 to the x, by making a table of coordinates and then graphing on the template here. So our function I filled in here, 1/4 to the x, and I picked some negative x values, 0, and some positive x values. And so if we take -2 and plug it in for x here and here, so that's saying take 1/4 and to the -2 power. And remember, negative exponent takes a reciprocal, so this is the same thing as 4/1 to the +2, which is 16. So that's going to give us the order pair -2, 16. So 2 to the left and 16 up, which is off the template here, so we can't graph that one. Plug in -1, so h plug in -1 will be 1/4 to the -1. Again, -1 means take a reciprocal. That's 4 to the +1, which is 4. So x is -1, y is 4. So -1 up 4 right there. 0. H plug in 0, 1/4 to the 0, anything to the 0 power is 1. And so we've got 0, 1, which is right here. 0 left and right, 1 up. Plug in 1 for x, so h of 1 is 1/4 to the 1, that's just 1/4. So 1 to the right, 1/4 up. So 1 to the right, 1/4 up, about right there. And then x equals 2, so we plug that in here, 1/4 squared. 1/4 times 1/4, 1/16. So we go 2 to the right and then 1/16 up. So 2 to the right, 1/16 up, about right there. And then we play dot to dot, connect these guys up. Well, almost. And we have a horizontal asymptote, the x-axis, and then this keeps going up faster and faster as you go to the left. So that's our graph. That one's all set. They just want us to do the graph. And in number 2, they want us to graph the functions 1/4 to the x and then 1/4 to the x plus 2 minus 1 on the same grid. Well, I already transferred over 1/4 to the x from up above. And we can graph this graph g of x here by shifting. So here we replaced x with x plus 2, so that's an inside replacement. And remember, when you do things on the inside, it does the opposite effect. So they say the inside's a liar. So doing x plus 2, remember x is a left-right shift when you do the replacement. This is going to shift the graph 2 units in the negative direction, so 2 units left. And when you add subtract numbers on the outside, then those work like they're supposed to. So this -1 is going to shift things down 1 unit. So I've already got the graph from up above. If yours is different, then you can plot the points to get the original graph. And then we want to take that graph, shift it 2 to the left and 1 down. So all these points will shift 2 to the left, 1 down, right there. Here, 2 to the left, 1 down. Here, 2 to the left, 1 down. And then this one, 2 to the left, 1 down. And then the x-axis, that was our asymptote for the original function. So now our asymptote is going to be the line y equal -1. I'm going to dash that in. So that line's going to get closer to y equals -1. And that graph's going to look like this. Okay, so there's our graph g of x. Let's see here, graph the equations of all asymptotes, and we did. We just got that one horizontal asymptote. So g of x can be obtained by taking the graph of f of x here and moving it 2 units to the left and 1 unit down. So that's what we did to graph. And then our asymptote for f of x was y equals 0. And so our asymptote for g of x was y equal -1 because we shifted everything down 1 unit. So we're covered here. So you're going to do a similar exponential function. You'll have an exponential function here, and then this one's just going to be shifted. Just remember the inside numbers, they shift the opposite direction. So a +2 shifts negative direction, a -2 would shift positive. And number 3, we want to use the compound interest formula, which is a equals p1 plus r over n to the nt, and a equals p e to the rt. So that's the continuous interest formula, and we're going to calculate the following. I'm going to do a little bit of rearranging here. There we go. So A is the amount in the account, P is the principal or the start amount, R is your interest rate, N is the number of interest rate periods, and T is going to be your time in years. So here we want to find the accumulated value, that's A. Okay, so A is accumulated of an investment of $20,000, that is our P, so that's our start amount. For 10 years, that is our time, T equals 10, at an interest rate of 4.2%. So our R is going to be 0.042. So your interest rate has always got to be as a decimal. You don't want to do it as a percent. So first of all, they want us to do it compounded semi-annually. Go ahead and bring this guy up here. So I went ahead and transferred our values down here. P is 20,000, R is 0.042, and your T is 10. So if you're compounding semi-annually, that means that you have 2 interest periods per year. So that means that N equals 2. So semi-annual is N equal 2. So now we've got to plug into this formula. So this is going to be our P, which is 20,000. And then that gets multiplied by 1 plus, and then it's R over N to the NT. So our R is 0.042. We're dividing by 2, because there's two semi-annual periods in a year. And then to the 2 times T, and T is 10 years. So 2 half-year periods per year times 10 years is 20 half-year periods. And then you just key this in on the calculator. A nice calculator to use for that is the MyScript app. They make that for both Android and iPhone. Works really good on a tablet because you just write with your finger exactly like it looks here, and it does order of operations for you. So if you compute this in the calculator, you'll get 30,307 and 0.13. And then they want us to do it compounded quarterly. So quarterly here means that N equals 4 because there's 4 quarters per year. So that's this 4. So quarterly is 4 times per year. So everything else in this formula is going to be the same, except the 2 is going to change to a 4. So this will be 20,000, 1 plus 0.042 over 4, and then to the 4 times 10 power. And if we key that into the calculator, you'll get 30,372.65. And notice that this is a little bit higher than it was semi-annual, because if you compound more, you're going to get more money. All right, so let's look at what we got going here. The other 2 parts, compounded monthly, that's going to mean that N equals 12, and then we're doing compounded continuously. So monthly here, there's 12 months in a year, so N equals 12. So that means that this 4 here is going to change to a 12. So 20,000, 1 plus 0.042 divided by 12, and then the exponent will be 12 times 10, 120 power. So, you know, if you're doing it on if you're not doing it on the MyScript calculator, you want to make sure you put those parentheses in there. And you might have to put parentheses around your exponent too. So if you key this one in the calculator, you'll get 30,416.92. And notice the 416, a little bit bigger than 372. More compounding, it's going to give you a bigger accumulated value. And then continuous compounding, that's the other formula. Okay, so that's this one, PE to the RT. So remember, E is that irrational number. It's the base for the natural logarithm is what it is. We'll get to that a little bit later here. So, and they wanted to do it with, let's see, continuous compounding. We don't need a value for n. So I'm sorry, this actually should not be here. With continuous compounding, you just need your R, T, and P. So for us, this P is 20,000. And then times E to the R is 0.042. And then T was 10 years. So 0.042 times 10. So that's 0.42, e to the 0.42 power, and then times 20,000. And if you key that in the calculator, you will get 30,439 and 23 cents to the nearest penny. And notice again, a little bit bigger than part C. So as you increase your compounding, this is continuously compounding all the time. And that's the best that you can do. So that's compound interest formula. So that's pretty much just plugging in values. And just remember here, this is your N here is compounding periods per year. So it's usually 2, 4, or 12. All right, in number 4, we are looking at some exponential growth here, so we're going to have a little bit of fun with it. So Dr. Nefario here has developed this new growth theorem for the minions, so we're going to grow some more minions here. Despicable me. And they are multiplying like crazy now. So we've got this exponential function, f of x is 239 times 1.047 to the x power. So the 1.047 to the x, that's our exponential. And we're told that this models the population of the minions, f of x, in thousands. And this is going to be x years after 2003. So 2003, this corresponds to your x equals 0. And so now it says substitute 0 for x, and without using a calculator, find the population in 2003. Okay, so x equals 0 corresponds to 2003. Going to plug a 0 in there. So f of 0 is going to be 239 times 1.047, and then that gets a 0 power. Remember, anything to the 0 power is 1, so this is just 239 times 1, which is just 239, and that's in thousands. So 239,000 minions. So he's got a few minions sitting around. Okay, we're going to multiply them. So part B, we're going to grow some more with the growth theorem. So part B, substitute 15 for x, and that's going to find our minion population. We'll do it to the nearest 1,000 in the year 2018. So that's 15 years after 2003. So that's going to be f plug in 15. So this 0 is going to change to a 15. So now it's 239, 1.047 to the 15 power. And if you plug that one into the calculator and round to the nearest 1,000, you will get 476. So it's not 476 exactly, but that's after rounding. So that means that the minion population here is going to be 476,000 in 2018, 15 years later. So we more than doubled our minion population. That's a lot of minions. Put them to work. Now they want us to find the minion population. So that's finding an f of x value again to the nearest 1,000 in the year 2033 as predicted by this function here. Okay, so 2033, that's going to correspond to x equals 30. And the way we get that is 2033 minus the start year 2003 is 30, so x is 30. So we're doing f plug in 30. So this 15 now is going to change to a 30. So 239, 1.047 to the 30 power. And we're going to go ahead and round that to the nearest 1,000 when we do it. So if you plug that into the calculator and then round to the nearest whole number, you'll get 948. So 948,000. So our minion population is going to be 948,000. And again, if you're using the MyScript calculator, you can just write this with your finger and it'll compute it for you. Works real nice. What appears to be happening to our minion population every 15 years? So notice we started with 239, okay, and then it just, it approximately doubled. Because like 2 times 239 is 478, and this is 476. And then notice 2 times 476 is 952. Here we're 948, so it almost doubled again. So it looks like our population approximately doubles every 15 years. So in your problem, look for a pattern like that, like doubling every same number of years, whatever they give you. I did 0, 15, 30. They might do 0, 10, 20 for you guys. But just see if it's not, doubling or tripling every so often. Okay, so that wraps up the minions. Got plenty of minions running around. Too bad we can't train them to do our math for us here, huh? Number 5, this is a real quickie. We want to write the equation in the equivalent exponential form. So 8 is the log base b of 15. So we want the exponential form. So b is our base. So that's the base for the exponential. And I like to read this as 8 is the exponent over b. So log base b, I read that as exponent over b. Exponent over b. So 8 is the exponent over b that gives 15. So here's b. And 8 is the exponent over b, and it gives 15. Another way to think about that is exponentials and logs. These are like inverse functions of each other. So here the 15 was the input and the 8 was the output for the log function. So here the 8's the input and the 15's the output. Okay, so this is the equivalent exponential form. So no work to show there. Just switching back and forth because exponentials make more sense to us. And then number 6, we're going to put some of these log functions to work here. So in the figure below left, this one down here, we've graphed log x. And remember that log means log base 10 if they don't write a base down there. And we want to use transformations of this graph to graph log x plus 3. So we added 3 on the inside. Remember, insides work as opposites. Okay, so if you do something on the inside, it's a liar. So this is saying plus 3, you're going to move minus 3. So you're going to go 3 to the left. So this is going to be 3 left. So you're going to take that log function and shift it to the left. We're going to determine domain and range below, and then use our coordinate template to graph. So log of x is already graphed for us here. Now if you have a graphing calculator, you can graph that on your graphing calculator. If you don't have a graphing calculator, then one thing that you could do is you could go to desmos.com. So that's this site. Up here you can see DESMOS. So it's desmos.com. And then right here is where you type your function that you want to graph. So we want to graph log x. We just type y equals logx. And boom, here it is. It's graphed for us. So we can see that the y-axis here is a vertical asymptote. And you can click this and you can just drag it around if you want to see different parts of the graph here. And actually it's off to the side so you can't see it good, but you've got a zoom in and zoom out button. So that's desmos.com again. So that's a real nice one. So that's this graph here. Now I did plot some points on there, 10, 1, because if you remember this log is really log base 10 of x. So this is the exponent over 10 that gives x. So the exponent over 10 that gives 10 is 1. If you plug 5 into our function here, you're going to get log of 5 in your y-coordinate there. If you plug 1 in, the exponent over 10 that gives 1 is 0 here. 10 to the 0 is 1. So if you do 10 to the y-coordinate, you get the x-coordinate. That's the relationship. That's the same relationship as logs. 10 to the negative 1 is 1/10, so that gives the point 1/10 to the right, down -1. So there's our log function. And our vertical asymptote is x equals 0, the y-axis. So we now want to do log of x plus 3. Okay, so that's going to shift things to the left 3 units. So we're going to take this point 10, 1, we're going to shift it 1, 2, 3 to the left. It's going to be 7, 1. So 3, 6, 7. Oh, and I've got these labeled. This must be 1 here. Oh, I'm sorry. If we're doing scale in half units, 10, -1 would be right there. Okay, so this will be our -1, this will be our +1, and then on the horizontal scale we're going to do 1, 2, 3. So these are whole units on the horizontal, but they're half units on the vertical. So I stretched it out a little bit. So we're going to take that 10, 1, shift it to the left 3 units. So 4, 5, 6, 7. So 7, 1 right there. And then 5 and log base 5, so that's going to go to the left 1, 2, 3 units. So it's going to be 2 and then up to log 5. So 2 up to log 5. And then this guy's going to go to the left. Oh wait, did I do it 3 units? 1, 2, 3. Yeah, I did. Okay, and then this guy's going to the left 3 units. 1, 2, 3. So that's going to be right here. So that's -2, 0. And then this guy's going to go to the left 1, 2, 3 units right there. So that's going to be right here. And then if you play dot to dot with these guys, then we now have as a vertical asymptote this line here. So instead of the y-axis, it got shifted to the left 3 units, which is the line x equals -3. So there is our vertical asymptote. And then they also want domain and range down here. So for this function, notice there's no graph to the left of -3. So our domain is going to be x greater than -3. In interval notation, you do -3 to infinity. But our range, well, the y value is hit by the graph. This keeps going down, and then this side keeps going up. So our range will be -infinity to infinity. Everything gets hit there. Okay, and I think we've got everything set there. And you can double check this on Desmos. So if we go back here, we'll just take and we'll insert a parenthesis here. And now we'll do a +3. And notice that it shifted this guy over, and now x equal -3 is your vertical asymptote. And then if we did it the other way, instead of +3, if we did -3, then notice it shifts it to the right. So a negative shifts right and a positive shifts left. So don't be afraid to use technology to help you out there. But understand the process. All right, number 7. Let's see here. Percentage of adult height attained by a boy who is x years old can be modeled by this logarithm function. And x is the age, and it's only from 6 to 18. So this model only works from age 6 to age 18. F of x represents the percentage of the adult height. And we're going to use that function to determine the approximate percentage of the adult height for a boy who's age 16. Okay, so that's in this domain, and that's going to be x equals 16. Round answers to the nearest 1/10 of a percent. So what they're saying is that x equals 16, and we want to go ahead and plug it into our function. So this is going to be f plug in 16 is going to be 66 plus 30 times the log of x minus 5. So that's 16 minus 5. So that's 11 to the log of 11. So you'd want to key that into your calculator. 66 plus 30 times the log of 11. And if you do that and round it to the nearest tenth, you get 97.2. So that's going to be 97.2% of the adult height. Okay, so that one's just a plug-in into the function. So you'll have a similar function that you'll have to plug in. And number 8 here, I got my algebra class and they took a final exam, and they were doing this experiment to see how much of the course content they're going to remember over time. And so they took equivalent forms of the exam in monthly increments after they took their final to see how much they remembered. And then the average score is given by this function f of t, and that's t months after they took the final, and that was modeled by this log function, 79 minus 14 log t plus 1, and it's only for t values 0 through 12. Okay, so we're only tracking out to a year. What was the average score on the original exam? So the original exam was taken at time 0. Okay, so original here, that means t equals 0. So we're going to plug that in. That's f of 0, and that's going to be 79 minus 14 times the natural log of 0 plus 1, so just natural log of 1. But the natural log of 1 is 0, so this is just 79 minus 0, which is 79. So 79 was our average score at the start. What was the average score after 1 month? So that's saying t equal 1, so they want us to do f of 1, and then 3 months in 1 year. So that'll be f of 3, and then f of 12. So f plug in 1, so we're going to plug a 1 in here for t. So that's going to be 79 minus 14 times the natural log of 1 plus 1. So that's log of 2, 79 minus 14 log 2. And notice that this is log ln, the natural log. So that's the log base e. So that's going to be a different button on your calculator. And I believe the MyScript calculator will do that too. So if you compute this on the calculator, you get 69.3. So their score dropped from 79 to 69.3 1 month later. 3 months later, then we're going to plug in 3 here for t. So 79 minus 14 log 3 plus 1. So subtract off 14 log of 4. And if you compute that one, so this is going to be 79 minus 14 times the natural log of 4. And that gives you 59.6. So they're retaining less. It's dropping over time. And then the last one, f of 12, would be 79 minus 14 log 12 plus 1, which is 79 minus 14 natural log of 13, and then that one turns out to be 43.1. So it makes sense that these guys are dropping over time. So your problem would be similar. It's, we're just plugging in here, plugging into that log function that models the change in the score. And number 9 here, we're going to use some properties of logarithms to expand. So we're going to expand the logarithm log base 3 of 27 over x squared as much as we can. So we've got a division inside the log here. And remember, division inside the log is subtraction outside. So this is going to be log base 3 of the top, 27, minus log base 3 of the bottom, x squared. Okay, and this is, I like to call this, division inside the log equals subtraction outside. That's one way you can remember that property. And then let's see here, exponents factor down. So this inside exponent can come down in front. And then the exponent over 3 that gives 27, this is just equal to 3. So that's actually going to be 3. And then this 2 will come down in front, minus 2 log base 3 of x. Okay, inside exponents factor down is that second property. And that one's done. So it's expanded. Didn't get a numerical value because we don't know what x is. And in problem 10, we're going the other way. So we want to use properties to condense. So now we want to put things back together. The expression log 3x minus 1 minus log x plus 2 plus log x. And we want to write it as a single log, condense it to a single log. So we're going to work left to right because of order of operations. So subtraction outside is division inside. So this minus is going to be division inside. So this will be the log, and this is log base 10. Yours might be different base. And then this will be the top and the bottom of the fraction. So this will be the log of 3x minus 1 divided by x plus 2. So I divided inside the log. And then we've got plus log x on the end. And then remember, addition outside the log is multiplication inside the log. So now we can combine these to a single log. It'll be log of 3x minus 1. And then we're going to multiply that by the x on the inside. And then divide it by the x plus 2 still. So division inside is subtraction outside. Multiplication inside is addition outside the log. So those are our properties. We can pull things apart or we can put them back together. In problem 11, we are doing an application of logarithms, looking at the Richter scale. So you'll have a similar application. So the formula for the Richter scale is log of A minus log of A0. A stands for amplitude of an earthquake in watts per square meter. And A0 is going to be the amplitude of what they would call a standard earthquake. And that's an earthquake that has amplitude 1 micron. So a micron's a millionth of an inch. Okay, so it's basically they're comparing it against the smallest earthquake that you could feel is what it is. So we want to express the formula so that the expression in parentheses is a single log. So they want us to combine things. So we've got subtraction outside, that's going to be equal to division inside. So we can just write this as log of, and this will be top and bottom, A divided by A0 inside the log. So that one's combined. And then we're going to use the form of the formula in part A to answer the following question. So if an earthquake has an amplitude 1,000 times a standard earthquake, what's the magnitude on the Richter scale? Okay, so that's saying find the log of A over A0. So evaluate this thing. Well, what's the amplitude of our earthquake? Well, it's 1,000 times as big as A0, the standard earthquake. So this is going to be the log of 1,000 times A0 on the top, divide by A0. But then these guys cancel, so we're just finding the log base 10 of 1,000. And you can enter that into your calculator, but this is the exponent over 10 that gives 1,000. That's just 3. 10 cubed is 1,000. So that's how I'm doing that in my head. Okay, these are equivalent expressions. So, but you can get this on your calculator. Just make sure you're doing LOG and not LN. So you'll do a similar application in your homework. All right, moving along, number 12. So we've got this formula in terms of logs. T is 1 over k log m plus a minus log m minus a. And that describes the time t in minutes that it takes to memorize a sequence of a digits and the cap m represents the maximum that a normal person can memorize. And then this k here, that's a constant that's used to measure the individual person's memory recall ability. So we want to express this formula. So we've got a single logarithm. Okay, so again, subtraction outside the logs is division inside. So using that property again. So we could write this as 1 over k. And then this one uses ln, natural log, so ln. And this will be log of the top minus log of the bottom. So we got m plus a on top. And then m minus a on the bottom. So we've combined to a single log. So that's what they wanted there. And then if a typical person can memorize a maximum of 45 digits, so that's saying cap m equals 45, then we're going to use this formula that we did up here to answer the question, how many minutes will it take to memorize 30 digits? Okay, so that 30, that's our A, cap A, right here, A digits, time to memorize A digits. And we have, let's see, we have 5 digits memorized. No, let's see, I don't think that's supposed to be there. We just want to have, sorry about that. We just want to know that k equals 0.15. So I've given this k to you. So we got k is 0.15, m is 45. This is just a plug-in here. And yours is the same. You're just doing a plug-in. So we're doing 1 over 0.15, natural log. Our m is 45. Our a is 30. So on the top, this is going to be 45 plus 30. On the bottom, it's going to be 45 minus 30. So that is 1 divided by 0.15. On the top, you've got 75. On the bottom, you've got 15. 75 over 15 is 5. So this is 1 over 0.15 natural log of 5. So that's what we're finding there. So you plug that in on your calculator, and you will get approximately 10.7. And that'll be minutes. So yours is similar. You're going to first combine to one log, and then you're going to do the plugins with the numbers that they give you. All right, 13. Here we're solving an exponential equation. 12 e to the 2x is 98. And we're going to express our solution in terms of natural logs or common logs. So they want an exact solution here to this thing. And then we'll obtain a decimal approximation to 2 decimal places. So, whoops, I'm sorry. 2 decimal places here, getting ahead of myself. So what you first want to do is isolate this exponential. So we want to divide the 12 off both sides. So we get e to the 2x then is equal to 98 over 12. And then the 98 over 12, you could reduce that if you wanted to. But I'm just going to leave it. And then we want to undo this exponential, and the opposite of an exponential is base e is a natural log. So take ln on both sides. And then since these are inverses, they're going to cancel each other out. So we get 2x is equal to the natural log of 98 over 12. And then divide both sides by 2. Which is the same as multiplying by 1/2. So that cancels out. So then our x is 1/2 natural log 98 over 12. So that's our exact answer. and then they want the 2 decimal place answer. So if you plug this into the calculator to 2 decimal places, that's approximately 1.05. And we got it. So exponentials, isolate the exponential, and then take logs on both sides. Okay, so isolate first. Got to put it in timeout, like it misbehaved. All right, problem 14, solving a log equation. Log root 2x minus 1 is 1. And we want to reject any x value that's not in the domain. So remember, logs, you can't take a log of a negative number. And we're going to give an exact answer in 2 decimals. So just like we did up above. So we've got, our log is already isolated here. Okay, so that part's all set. So then you undo logs with exponentials. So e to the natural log of root 2x minus 1 will equal e to the 1. So we exponentiate on both sides. E and ln cancel, so they're gone. So now we've just got that root 2x minus 1 on the left and equals e on the right. So now we want to undo the square root, so we'll square on both sides. So then the square and the square root, they cancel out their inverses. So we get 2x minus 1 is equal to e squared. Now bring the 1 over as a positive. So 2x is going to equal e squared plus 1. And then divide by 2 on both sides. So these 2's cancel. We got x left is e squared plus 1 over 2. And then you can enter that into your calculator and get the approximation. So when I did that, I got 4.19. So approximately 4.19 to 2 decimals. So, and you double check me on that. All right, problem number 15. We are given the formula A is 17.3 e to the 0.00315t. That models the population in the land of Oz. A is our population in millions, and T is T years after Dorothy arrives in 1940. So going on a little trip to Oz. So we want to know, what's the population of Oz in 1940? Well, in 1940, T equals 0. So that's our start time. So you're just going to plug 0 in here for T. So it'll be 17.3 e to the 0.00315 times 0. But then this is just going to be e to the 0 power, and e to the 0 is equal to 1. So we get 17.3 times 1, that's just 17.3. And that's in millions. So 17.3 million. 17.3 million little munchkins. Munchkins and witches and tin men and lions. And we want to know when, so that's a time, when will the population of Oz reach 25? So what we're going to do is we're going to take the population A, which is this 17.3 e to the 0.00315t, and set it equal to 25. And now we want to solve that exponential equation. So first we got to isolate the exponential, and then we're going to do logs on both sides like we did up above. So we will divide by 17.3 on both sides. And so these guys cancel. So we get e to the 0.00315t equals 25 over 17.3. And then we want to undo an exponential. So we're going to do a log on both sides. So natural log on the left, natural log on the right. These guys cancel because they're inverses. So we now have on the left-hand side just 0.00315t. And on the right-hand side, we've got that natural log of 25 over 17.3. Probably need some parentheses here for a calculator. And now I want to solve for t, so we just divide off that constant, 0.00315 on the left, and either divide by it or multiply by reciprocal on the right, 0.00315. These guys cancel. We get t equals. So this is our exact answer. And then if you plug that into the calculator, you will get approximately 117 rounded to the nearest whole number. So that's going to be years. And that's after 1940. So they're asking when? Well, 117 years after 1940. So 1940 plus 117, 117 years later. So that's going to be in the year 2057. So I got to wait till 2057 before Oz reaches 25 million. So they're growing a little slower than the minions were. All right, we're getting there. 4 more. So here we're given a function f of x is 22 times 0.885 to the x, so exponential function, and that models the percentage of surface sunlight f of x that reaches a depth of x feet. So x is the depth below the surface of the ocean. So as you know, the water filters out some of the light as you get lower. So this is the percentage of surface sunlight that reaches down there. So, because I mean, if it didn't diminish, you could go down like 1,000 feet, and you could see everything light as day. But if you go down 1,000 feet, you won't be able to see your hand in front of your face because all the light gets filtered out. So, so I didn't graph this one. It says the figure below gives the graph of this function. Use the function to determine the depth to the nearest foot, so that there's 3% surface sunlight. So 3% is going to be 0.03. So that's the fraction of the original sunlight left. And how is this shown on the graph? So if you graph this thing here, remember, exponentials go up from left to right, and this one's not shifted, so it's going to have a horizontal asymptote of the x-axis. And then when x equals 0, this is 22 times 0.885 to the 0, which is 22 times 1, which is 22. So when x is 0, it's going to be at height 22, so it's going to start here at height 22, and it's going to go up. So the exponential going up like that, and then this side's going to come down and asymptotes the x-axis. But this is really not in the domain here, okay? Because x is a number of feet below the surface. That's going to be a positive number. So it's really the right-hand part here. That's our graph right there. So we want 3% below the surface. And oh, I'm sorry. This is the percentage of the surface sunlight. So the 3% is actually going to be a 3, not a 0.03, when we do our solving. Okay, so that's our f of x value is 3. So we are determining depth, which is x. So what we want to do is take our f of x right here, 22 times 0.885 to the x, and set it equal to 3, that 3%. And now we want to solve this equation. So we first want to isolate that exponential here. So let's divide 22 on both sides. And now we're left with 0.885 to the x power is equal to 3 over 22. And now we want to find the x. We want to get it down out of the exponent. You do that with logs, and you can do ln or log, whichever one that you prefer. Let's see here. I decided to use ln, but you can use log and it also works. And then property of exponents. that guy comes down in front. So exponents factor down, so we get x times the natural log of 0.885 is equal to ln of 3 over 22. And then we want to solve for x, so we want to divide that off of both sides. Give myself a little bit more room here. So we're going to divide by ln 0.885. And then these guys cancel. Log of 0.885 is just a number that cancels off, and x is our depth. So that's this guy here. So you plug that into your calculator, make sure you use parentheses on the top there. And when I plugged that in, I got approximately 16.3. And that is, let's see, that is feet. Okay, so 16.3 feet. So at 16 feet below the ocean surface, we've got 3% of the sunlight left. That seems like that model is off a little bit, but I just made this problem up to be similar to one you guys had. I think you'd probably have more than 3% light at 16 feet. I think you'd have to go down quite a bit more to get only 3%. So you guys will be doing something similar here. Taking logs on both sides, you'll bring your exponent down, divide off the coefficient. And then let's see, how is this shown on the graph of f? Okay, so that's saying when x is 16.3, then your y is equal, let's see here. So if x is 16.3, oh, you know what? 0.885, that guy goes down from left to right, because our base here is less than 1, and then that graph decreases from left to right. So it does go through that 0.22, but it goes down from left to right, like this. And then this point is, if you go out to 16.3, and you go up and over, then that's going to be height 3. So that point right there is 16.3, comma 3. And you can see this too, like if you go to Desmos and you graph this. So let's do y equals, let's see here, y equals 22 ln, and then we, or I'm sorry, not ln, 22, and then we have parentheses 0.885, close parentheses, and then I think we want to do a caret. Nope. That didn't work. Let's see. Exponents here. There we go. So I hit a little key at the bottom that popped up this keyboard, and I want, now that's squared, I want an x exponent. Oops, there we go. Get rid of that keyboard. Okay, so this hits at 22, so I need to zoom out to see this graph. There we go. So it's hitting up here at 22, going down from left to right. Okay, so that's the graph that I drew. And number 17, we are looking at another exponential model. This describes the population in a country, A in millions, and T is years after 2010. So 2010 is your time zero. So in Syria, the population is 37.5 e to the negative 0.018 t. Greece, it's 11.3 e to the negative 0.005 t. France, 57.2 e to the 0.011 t. And China, 1340.5 e to the 0.004 t. And they ask us here first, what's the population of Syria in 2010? So 2010 is times 0. So this is t equals 0 because it's t is years after 2010. So this is start time. So Syria in 2010 is going to plug in 0 here for t. So it's going to be 37.5 e to the negative 0.018 times 0. Well, this will be e to the 0 power, which is 1. So that's 37.5 times 1, which is 37.5 million. So 37.5 million at the start. What's the population of France in 2018? So that's time 8, because that's 8 years after 2010. So we're going to take the France formula here, 57.2 e to the 0.011 t, and we're going to plug in 8 there. So 57.2 e to the 0.011 times 8. And then we plug that into the calculator. So 8 times 0.011 is 0.088. And if you plug that guy in, you get I had already done this ahead of time, 62.5 to one decimal place, and that's million. So population of France increased from 57.2 to 62.5. Which country has the greatest growth rate? And by what percentage is the population of the country increasing? So the growth rate is this coefficient of t. So notice that Syria and Greece, they have negative coefficients. Their population's decreasing. Syria because of the war, and Greece because of their financial crisis. But France and China, theirs are increasing, and China's is bigger, 0.011, which is 1.1%, or 0.004 for China, 0.4%. So country that has the greatest growth rate is France. And our rate, R, is 0.011, which is 1.1%. So they're growing the fastest. Which countries have decreasing population? So we already mentioned there, Syria and Greece. And by what percentage is the population of these countries decreasing each year? So for Syria, negative 0.018. So this is negative 0.018 is that coefficient, which is negative 1.8%. Move the decimal 2 places to the right. For Greece, it's negative 0.005 here. And move the decimal over 2 places, so that's negative 0.5%. So it's losing 0.5% per year. And then last part of this question, when, so that's asking for a t-value, when will China's population reach 1,500 million? So that's 1.5 billion. So you're going to take the equation for China's population right here, brought that down, and set that equal to 1,500. And then you want to solve for t. So, well, we've done several like this now. You want to isolate that exponential. So divide off the 1340.5 on both sides. And these guys all cancel. So we're left with e to the 0.004t is equal to 1,500 over 1340.5. We want to undo exponential, and that's e, so we'll undo it with ln. So take ln on both sides. So the cancellation law for logs and exponentials, those cancel. So we get 0.004t is equal to this log And probably want to put that guy in parentheses. And then we divide off the 0.004 on both sides. And that gives us our t. So these guys cancel, and t is now all by itself, this guy here. So if we plug that into the calculator, so I did that, and I got 28.2. So approximately 28, and we would add that on to 2010. So 2010 plus 28, 2038. Okay, so you'll be doing something similar with it. All right, problem 18, we are looking at radioactive decay. So we found this artifact that originally had 55 grams of carbon-14, and the decay model they give us is 55 e to the negative 0.000121 t, and that describes the carbon-14 t years after t years. We want to know how many grams of carbon-14 will be present in 3,425 years. Document calculations. So that's just saying t is, this is a t value, and they're just wanting you to plug that in here. So I brought that formula down, 55 e to the negative 0.000121, and then our t is 3425. And so we multiply that, and then do e to that power, and then times 55. Or if you're using, if you're using a graphing calculator or MyScript, you can just type it in just like that. So I typed that into my calculator, and I got approximately 36.3. And that's going to be grams. So that one is basically just a plug-in. Okay, so your number 18, that should be just a plug-in. And let's see, in 19 here, we're going to use the exponential decay model. A is A0 e to the kt. A0 is your start amount. K is the decay rate, and T is time. The half-life of oxygen-15 is 122 seconds. And we want to know how long will it take for a sample of oxygen-15 to decay to 30% of the original amount, round to 1 decimal. So what we're going to do is we're first going to use the half-life to get the constant. So the half-life is 122 seconds. That means after 122 seconds, you've got half as much. So your A0 is your initial amount. So if you initially start with 100%, which is 1, then your formula is A equals 1 e to the kt. And we know that our time here for the half-life is 122 seconds. So I plug that in for t right here. So now it's e to the 122 times k. And we set that equal to 0.5, 1/2. Because half-life means half as much is left. So 100% down to 50%, which is 0.50. So now we've got to solve for that constant k. So now we've got e to the 122k equals 0.5. And you undo exponentials with logs. So do natural log on both sides. These guys cancel. So we get 122k equals log of 0.5. Divide off that 122. So those guys cancel, so that's our constant k. So log of 0.5 divided by 122. And that is, if you key that into the calculator, that's approximately negative 0.00568. I want to carry that out a few decimal places. So then what that means is that's our constant that goes in here, k. So now I updated our equation. So our equation is e to the negative 0.00568t. So I plug this in for our k. That's k. and I'm using for my A0 1. So there's a 1 here that I didn't write. And now they ask us here now how long. So how long is asking for a time. How long will it take for a sample of this substance to decay to 30% of its original? Well, it starts with 1, which is 100% of its original. 100% is 1. And it decays to 30%, which is 0.30. So we're going to take this thing and set it equal to 0.30. So now we've got e to the negative 0.00568 t is equal to 0.30. And now we've done this a bunch of times. How do you undo e? ln. So take natural log on both sides. These guys cancel. So we get negative 0.00568 t equals ln of 0.3. And now we want to divide off that coefficient on both sides. So divide both sides by 0.00568. Negative. These guys cancel. So we get t is, plug this in the calculator. I got approximately 212.0 to the nearest tenth. So, and that's what they wanted was 1 decimal, and that's seconds. So 212 seconds to go from 100% down to 30%. All right, and last one. Here we've got a table down here, years after 1980, and then the mean college tuition, so public. So we're looking at public college tuition for a year. In 1980, it was $3,100. 30 years later, by 2010, it gone up to $10,500. They want us to create a scatter plot and then use the scatter plot to determine if an exponential function, logarithmic function, or a linear function is the best choice for the model. So scatter plot just means that use this as your x and use this as your y and graph them. Okay, so I just sketched, let me bring our table down here. So we just want to graph this guy here. So in my x, I've got years after 1980, and my y, I've got college tuition and going up in thousands. So I skipped a little bit of the scale down here just so that I can concentrate on this data. So time 0, we're at 3,100. So 0, 3,100, about right there. 10 years, we're at 4,700. So 10, go up to 47, about right there. 20 years after 1980, it's 2,000. We're at 7,300. So 20 up to 7,300, about right there. And then 30 years, we're at 10.5. So 30, we go up to 10,500, a little higher than 10,000, about right there. Okay, and they want to know, is it exponential, logarithmic, linear? So, well, it's not linear, okay, because if it was linear, these would all go through a straight line. Okay, and the straight line through the first two, it doesn't. These guys go up. So it's definitely not linear. In fact, if we connect these points here, looks like it's curving going up like this. That looks like an exponential function. See if we continued this here. So this is exponential. So remember, exponentials look like this, and logarithm functions look like this. They're curved down where exponentials are curved up, unless you got a minus sign in front of them. So that's all you need to do for that one, was just do the plot of x and y, and then just notice that it's not linear, it's not logarithm, it's exponential. It's this guy right here. All right, so that should put you in good shape to complete the homework from session 5.